In this class, we'll talk about the first of three different research situations in which we can use the t-statistic to evaluate hypotheses concerning differences between groups by looking at differences between group means. The first way we use the t-test to test means is the exact situation we used as an example in an earlier class when we used the z-test. Let's revisit the example. We said that we selected a single sample from the population of adults suffering from depression and provided them with an experimental therapy for depression. And we decided to see if there were differences in depression at the end of treatment by using the Beck Depression Inventory and scores on the Beck Depression Inventory to measure depression. In that example, we imagined that the mean of the Beck Depression Inventory in the population of depressed adults was 17. Our research hypothesis was that the experimental group would have a lower mean score on the Beck Depression Inventory than the population mean at the end of treatment. And our null hypothesis was that there would be no difference between this group mean and the population, and that the mean of this group would equal the population mean of 17. If we knew the variance of the population, we could use the z-test to evaluate this hypothesis. But let's say we don't know the population variance. As a result, we'll need to use the sample variance as an estimate of the population variance and the sample standard error as an estimate of the standard error of the mean in the population. The actual formula we use looks very much like the z formula in that we subtract the population mean from the sample mean. But this time we divide the sample, we'll divide by the sample standard error of the mean instead of the standard error of the mean in the population. The big difference between the population and sample standard error is that in the latter we'll rely on the sample variance rather than the population variance to compute it. And remember that the sample variance is measured or is computed with n-1 in the denominator, or degrees of freedom in the denominator, not n. Once we have a sample variance, we can compute the standard error by dividing the sample standard deviation by the square root of the sample size. Because we are working with a one sample mean, degrees of freedom will be equal to n-1. So the number of participants minus 1. Before going to the next slide, see if you can answer this question. Let's say the sample mean remained 12, but the sample variance in this experiment had turned out to be 121. Please compute the sample standard error of the mean and then compute the t-statistic. The answer is that the sample standard error would be 2.2. We would take the square root of the variance and then divide that by the square root of the sample size. Thus, 11 divided by 5 equals 2.2. And this would be our estimate of the sampling error in our study. To compute the t, we would subtract 17 from 12, which is a -5. We will think of this number as the effect of the treatment associated with participating in the group. If we then divided the treatment effect by the estimate of sampling error, we wind up with the t-statistic equal to -2.27. Before going to the next slide, see if you can answer this question. If the t-statistic is -2.27, do we accept or reject the null hypothesis? From the table, we learn that the critical value is equal to plus or minus 2.064 when alpha is equal to 0.05 and we are using a two-tailed test. and degrees of freedom are 24, or which is equal to 25 minus 1, or n minus 1. Thus, the test statistic is equal to negative 2.227 and is greater than the critical value of t equal to plus or minus 2.064. And as a result, we would reject the null hypothesis. We would then conclude that the mean for the experimental group is lower than the mean of the population. We would also assert that if we did this experiment 100 times, we would expect to observe a mean for the experimental group that was actually equal to or greater than the population mean in fewer than 5 of those experiments. Note that the critical value for t is always higher than the critical value for z unless t has an infinite degrees of freedom. This means that for every test of t, it will be more difficult for us to reject the null hypothesis than it would be for the same test using z. By this, I mean that we need to have a higher t statistic to reject the null than if we were using a z, where the critical value is always plus or minus 1.96. Thus, for any test where we need to use t instead of z, we are using a less powerful test. So, hearkening back to our discussion of power earlier, in addition to the sample size, alpha, and error, another factor that affects the power of our hypothesis testing is the type of statistic we use, with the z-test being more powerful than the t.